welcome everybody. Today we're going to be talking about recursion. So recursion is when a function calls itself. Okay. So if we have a function main, and main calls a function called foo, and main calls foo like this. If foo calls foo, then we have an infinite loop. Right? Because main's going to call foo, foo's going to call foo, it's going to call foo, which is going to call foo, which is going to call foo, which is going to call foo infinitely. All right? So recursion is, you can think of it almost as an alternative to doing a normal loop. So the way that we normally do recursion is we will do something like this, where we'll say if x is less than or equal to 0, return, and here, and here. Okay. So if we see out hello world, let's just do this with like a 4 here. What's going to happen is main is going to call foo passing in the number 4. We check to see if we're done. This is something called the base condition. Okay, base case or base condition. This thing stops the infinite loop. Okay, it's going to count down every time. Right here, when we call foo of 4 is going to call foo of 3. This is what stops it. The base case, the base condition is what stops it from looping forever. There are two things that you have to do in recursion to stop it. Every recursive solution needs two things. It needs one, a base case to stop the infinite loop, and it needs an inductive step to always move towards, there's maybe a small little asterisk on always, it could be probabilistically always, move towards the base case. Okay. So here we have no longer an infinite loop, we have an inductive step. So when we call foo of 4, it's going to check to see, are we done yet? No. So it's going to print out hello world. It's then going to call itself with foo of 3. Is 3 less than or equal to 0? No. So it's going to print out hello world again. And it's going to call foo of 2. So this is basically another way of doing a for loop. Okay? And so you can see here that we printed out hello world 4 times by doing it this way. I know computer science majors that were taught this instead of for loops. They were taught recursion instead of for loops as your basic way of doing something x times. In this case, x is equal to 4. And they just would write in a like recursive function calling itself, check the base case, subtract 1. Like this is just how they learned a for loop. Instead of for I equals 0, I is less than x, I plus plus, they do this. What do you guys think about it? Do you like it? Do you not like it? This is your basic inductive function. So this is okay. Seems cool, neat. All right. I personally don't like writing code this way. Seems extra complicated. I just use a for loop for sure. But like I said, there's some people, this is what they were taught in CSci 40. They weren't taught for loops until like CSci 41. They weren't, they were just taught recursion as the way of doing a loop. Doesn't it take more memory? Yes, it does. And we'll talk about that in just 1 second. So this is working fine for 4. What if we did this for 4,000? Works fine. What if we do this for 40,000? Works fine. All right. What if we did it for 400,000? Works fine. What if we had some variables here? What if we had integer array of size 1,000? It depends on what the optimizer is doing is actually the answer here. I think the optimizer might be outsmarting me a little bit. Yeah, there we go. The optimizer is keeping it from crashing. But what actually will happen if you recurse into yourself too many times is that you'll actually run out of what's called stack space, and I'll explain that in a second. And then your code dies. And it dies in such a way that it is unrecoverable. Running out of stack space results in an unrecoverable crash, because whatever code you could have that would recover from the crash would require stack space, and you don't have any stack space left and you'll crash. So what the hell is stack space, and why is this such a popular term? It's so popular, in fact, that the website Stack Overflow, which is what I just did, by the way, that was a Stack Overflow error, is actually the name of one of the world's most popular sites for abusing people for asking honest questions. So, sorry, it's supposed to be a website that is you can go to ask for help with technical questions. What it turns out to be, though, is just people telling you you're doing it wrong, you shouldn't do it that way, and then closing the question unresolved. So it is a toxic community. Okay, so let's talk about the memory map a little bit. This is going to maybe jump ahead a little bit, but it might be interesting for you. So imagine that this is RAM. Imagine that this is RAM. If I can draw a straight line, that's better. Imagine that this is a picture of RAM. At the very bottom of RAM, arguably, is memory address 0. And at the very top of RAM, arguably, it depends on your perspective, is 7FFFFF. Okay. So technically, the operating system lives down here in negative space, but we're not going to pay any attention to them right now. This is your program. Okay. So when your program runs, it has access, it thinks, to the entire span of memory on your computer. It doesn't, but it fakes it. It looks like it is. Okay. So down here at memory address 0, I'm going to actually just tell you where things are in memory. You will see me draw this memory map a lot in your computer science career. This is probably the first time most of you have seen me draw it. So the area down here, I call the minefield of doom. Apparently the technical phrase is the 0 page, but the reality of the matter is if you read or write to memory addresses around 0, then the operating system detects that you have touched a minefield and it explodes your program. So here's one way of getting a seg fault. We're going to do another way right now. So let's create an integer pointer that's set equal to 0, memory address 0, and let's just see out what is at that memory address. This will be fun. Let's find out what happens. Seg fault is what happens, okay? So anytime you read or write to any of the memory around the 0 page, around memory address 0, the operating system has that marked as non-readable, non-writable. So when you touch it, the operating system goes no, and it kills your program with what is called a seg fault, or a segmentation violation. Seg fault, and I got like some drippy S here. It's like Halloween S right there. Okay, so if you ever touch any of this RAM, it'll kill your program. If you ever go outside of any of the other segments, these are called memory segments, the operating system will detect it and also kill your program, because your program is doing something it should not be doing. Okay. Above the minefield of doom is what is called the code, sometimes called the text segment. And this is where your program is. So all of your assembly programming goes into RAM here. Okay. And so all of your program gets translated into assembly. All of that gets stuck into the text segment or the code segment, whichever term you prefer. Call this text segment if you like. And all of your assembly code goes there. And when your program runs for the first time, it finds main essentially and just starts executing the assembly there. Your CPU does not understand C++. Your CPU understands assembly for whatever kind of assembly your CPU uses. There are different kinds of assembly. If you compile your code on an x86 processor, you will not be able to run it on an ARM processor because they have a completely different assembly language. Okay. Above the code segment is something called the BSS, which doesn't stand for anything meaningful. And this is where your globals live. Okay. So all of your global variables live in the BSS segment. If we come up here, make a global, and we're going to call this guy int entry, because it's global entry. Huh? No? Anyone? Anyone here global entry? No? Okay, never mind. If I output the memory address of entry, let's take out that loop there. If I print out the memory address of entry, I'm going to get a memory address there. If I have an integer on the stack, it's going to be much higher in an address. Okay. And that is because the stack, which is where all of our regular variables live, is up here near 7FFFFF. So this is something called the stack. And when you run out of stack memory, you get a stack overflow error, which again is the name of a website that trolls people for not being as good at computer science as other people. Now there's one other area that is important, and that is called the data segment. Right here. The data segment can grow, actually. The stack grows downwards, the data segment grows upwards. And the data segment is where like your vectors and things like that live. So if we have a vector of integers named vec, and we see out vec dot data, a function call. Yeah, I know it's uninitialized. Okay. That's a null pointer. Let's see. Let's take memory address. All required vec.data is, maybe it's a null pointer because it's not allocated. Equals 10, 20, 30. So vec.data gives you a pointer to its internal. There we go. So you can see it is slightly above the BSS right here. So that is the vector. It's being held in the data segment. And the regular variable x is held in the stack segment up here near 7FFFFFFFF. Okay. So these apparently around 0.5 something or other F. What was it? 5.5 EC. And these aren't like really fixed values, but just kind of giving you an idea of where like things are. So the data segment has effectively unlimited memory for all intents and purposes. The stack on our system has an 8 megabyte limit. So how are we running out of stack space? Well, every time you have a variable, like we have x here, it takes up a little bit of room on the stack. Now, do you guys know how many bytes an integer is? Anyone know? How many bytes is x? Anyone know how many bytes a integer takes on our system? There's no actual fixed size to an integer in C++. You can actually have 16-bit integers under the standard. Does anyone know how many bytes, not bits, bytes, the integer is on our server? I see some people typing. Some people are typing. Joke answer. 4 bytes. It's a 32-bit integer. Okay. So what if we have a double? How many bytes is a double? Anyone know? It is 8 bytes. And so stack memory. Okay. So each one of these variables is going to eat up a little bit, a tiny little bit. 8 megs is actually more than enough for like normal usage. Like you're not going to have, you know, millions of, 2 million integers. Now I could make an integer array, and just make it of size 8 billion, right? I could do this. What do you think is going to happen when I do this? How much RAM does this take up? How much RAM does a million integers take? A million integers. How many megs of RAM? An integer is 4 bytes. There's a million of them. 4 megabytes, correct. Works fine. Why? I got more than 4 megs of stack. Yep. Let's kick it up a notch. It's now 40 megs of RAM. It's fine. Let's kick it up a notch. 400 megs of stack space. The system will actually allow you to exceed your stack space a little bit. Okay? Let's kick it up another notch. 1 billion. Segfault. Core dumped. Okay. And in fact, the optimizer is actually protecting us, because the optimizer knows we're not actually using all of that RAM. So the optimizer actually kept us from crashing well earlier. So let's see. Yep. There we go. So 4 megs works, 40 megs does not. Okay. So our stack is set at 8 megs. Sometimes it's not like a exact amount actually, but you can think of about 8 megs as being your limit. So if you want to have more than an array of size 1 million, you need to use a vector. So a vector, one of the other benefits of a vector, other than it's just better than an array in every possible way, one of the benefits of a vector is that vectors store almost everything. The only thing stored on the stack is actually the variable called vec itself. That's a few bytes. It's not, if you have a vector of size 1 billion, part of the vector...
Mommy is asking you to move your car in front of the garage because we're trying to go out and get Halloween decorations.
Okay, I will be right back. I have to move my car so that my family can get Halloween decorations. Be right back. So while I'm doing this, why don't you guys write FizzBuzz? FizzBuzz is a famous job interview question where companies will give you like 15 minutes to solve it. What you have to do is print the numbers from 1 to 100. Numbers divisible by 3, you print fizz instead of 3 or 6 or 9. Any number divisible by 5, you print buzz. Any number divisible by 3 and 5, you print FizzBuzz instead. I'll give you guys 15 minutes to do it. Time begins now. Okay, so one of the fun things about FizzBuzz is that it is not only a drinking game where people will go around in a circle clapping, going 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, buzz, 11, fizz, 13, 14, 15. Ah, dang it, 15. It's supposed to be FizzBuzz. Shot. Not only is it a drinking game, but it's also a kids game that will teach kids divisibility and things like that. And it's also one of the most common job interview questions that you can get. It's famous in computer science as a filtering question. It doesn't get you the job at Facebook, but if you can't do it, you will not get a job at Facebook. So it's a way of filtering out people that cannot code their way out of a wet paper bag. 15 minutes is sort of the standard time given to be able to do it if you wish to have a job in the industry. So here we have a version from Garza. It looks pretty good to me. If it's visible by 3 and 5, we print out FizzBuzz. Divisible by 3, we print fizz. Divisible by 5, buzz. Otherwise, nope, missing one thing here. We're not printing out the number, so you need to see out I in there. Otherwise, it's looking pretty good. I think if you do the input tester, because you're in a testing directory, I actually pushed out a FizzBuzz directory to you. So if you guys go online, you'll actually see you have a FizzBuzz directory. They become Garza. And so I gave you a lot of helpful code, a lot of helpful tips right there. Write your code here to do your lab time for today, and your lab time for today is going to be doing FizzBuzz recursively. So we're not quite there yet because I need to go over a little bit more of the what's going on and why it seg faults and things like that. So let's switch gears back to the memory map over here. And so the data segment, I'm going to call this the heap instead. There's like an RO data segment, which stands for read-only data. The BSS is often for uninitialized globals, and then they have like another data segment for like globals that are initialized and things like that. There's like some details in here, like there's different like little subcategories and stuff like that. It doesn't matter too much, but basically the upshot is your hash maps, all of those, like if you've got like 50,000, 100,000, a million things in your hash map, all of those things are going to be stored here on the heap. Okay. If you tried storing them on the stack, like we saw, we tried making that giant array, you very quickly run out of your stack space. Now I have the stack space configured at 8 megs. If you type a limit, you can see the size of your stack, and you can change it. And you might be like, well, isn't more stack better? Sometimes. A small stack is actually usually preferable. And the reason for that is because if your recursive functions get out of control, like if you are calling yourself too many times, having a smaller stack space means that you will catch your infinite recursion quicker, because it will kill your program quicker. Okay? So now if you're running out of stack space under normal operations, yeah, you should probably expand your stack space. I sometimes use like 100 megs of stack or something like that. But here it's going to use 4K of RAM every time it calls foo. So this is a stack allocated variable here. So this is on the stack. If you had a vector of size 1000, this is on the heap. The heap has effectively unlimited, you're talking gigs of RAM, right? However much your system could put up with. The stack, though, that's tiny, right? And it's tiny by design, so that your program will die quickly if you go out of control, if you infinite loop. So, so that's another reason why arrays suck. Now, it's faster to allocate things on the stack, and I'll show you why in a second. Let me just make a couple more. Let's get rid of this guy here. Integer A and float B and double C and char D. It should be char C. Okay. So these are all stack allocated, okay? All these things are allocated on the stack. So let me just get rid of the array so we have something a little bit more normal. So how many bytes, again, is an integer? You guys remember? It's on the screen. 4 bytes. Okay. How many bytes is a float? 4 bytes. How many bytes is a double? A double has double the precision, double the memory usage of a float. Is 8 bytes. And a character is, do you guys know how many bytes a character is? A byte is 8 bits, by the way. A character is sort of definitionally 1 byte. What about a Boolean? How much RAM does that take up? 1 bit? Bit's an eighth of a byte. Anyone know? 2? A Boolean on our system takes up 1 byte of RAM. Okay. So it actually takes 8 bits to hold 1 bit. Not because that's good, just because variables, the minimum amount of RAM you can allocate for a variable basically is a byte. So there are different data structures you can use that will bit pack. In other words, if you have like 32 bits in an integer, you can treat that integer as if it was 32 different Booleans. And there's a bit set in the standard library that does that for you. Most people just write it themselves because it's pretty easy. Probably by the end of like CSI 41, you'll know how to like bit pack an integer and treat it like 32 different bits. But by default, if you make a variable of type bool, you're going to be allocating 8 times as much RAM as you should be. So keep that in mind. And I've seen booleans take up 32 bits too, and that's wild. You need 32 bits to hold 1 bit. Okay, so how much RAM all told is this function going to use? Let me show you what it looks like on the stack. So we got a 4, a 4, an 8, a 1, and a 1. Yep. So let me zoom in on this area up here in the stack. So let me zoom in on that top part of RAM. Up here, of course, is the top of RAM at 7 F, 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 grade F, F, F for you, F for you. Yep. All the variables in main are like up here. So in main, we've got X and F and R. So we've got X is up here, and it's equal to, I don't know, 42 or something. I'm just making numbers up now. F is equal to 3.14. Then we've got this array that's like, I don't know, like a megabyte in size, right? And so you have something called the stack pointer. And the stack pointer holds the current address in memory that we're at on the stack. Every time you call a function, the stack pointer moves down. And it moves down a number of bytes equal to how many variables we need to allocate, the total memory cost of all of the variables we need to allocate. So if we're going to allocate, when we call foo down here, how many bytes down does the stack pointer have to move at a minimum to be able to allocate memory for A, B, C, and D? What's the total memory cost of calling this function? How much RAM does this function need? It needs 18 bytes, right? Because I don't have Bob highlighted here. It needs 18 bytes at a minimum. Now, it's actually going to be higher than that because you have to hold things like your return memory address and things like that. There's a little bit of like bookkeeping stuff that actually will get stacked on top of that. So it's actually going to be more than 18. We'll just say as a simplified rendition here, let's say that our memory address, our stack pointer is at memory address 150. And we just called foo. How far down does the stack pointer have to move? What's its memory address now? If it moves down 18 bytes in RAM. What's the memory address now? 168 doesn't sound right. That's moving up in RAM. We're moving down in RAM. Stack pointer is now pointing at 150 minus 18. 132, good. And this makes room for what I call them, A, B, C, and D. Yeah, A, B, C, D, and Bob. Okay. So this makes room for A and B and C and D and Bob. And then when foo calls itself again, the stack pointer moves down again 18 bytes. It moves down 18 bytes again. And so what memory address is the stack pointer at now? If it was at 150 before, after the first call, it moved down to 132. After the second call, what's the memory address again? And we have another copy of A, B, C, D, and Bob, right? Because one function call's version of A, B, C, and D is completely separate from all the others. If you change C in one function call, it doesn't call it in the previous function call. Each time you call the function, it gets its own set of A, B, C, D, and Bob. Okay. So what is 132 minus 18? 114. Good. Good. And then what does the function do? Well, it calls itself again. So the stack pointer moves down again, and it's going to keep moving down and down. So what is the memory address? What is 114 minus 18? Good. 96. Good. And it's just it's an infinite loop, right? So every time the function calls itself, it is going to be moving that stack pointer down and down and down. 18 bytes at a time, actually a little bit more. But But if we do this in an infinite loop, well, it'll segfault. Okay. So what happens here is that as you keep, you've got this little thing called the stack pointer right here. As that thing keeps moving down and down and down, eventually it exceeds some threshold. And that is the limit that your stack can cross, can get up to. Once you cross it, you get what's called a stack overflow, which means you have to tell people their code approach is wrong and they're asking a stupid question. That's the rule for stack overflows. Okay. And so this is one of the reasons why I avoid recursion. I avoid recursion because I'd much rather just do a for loop normally, right? I don't want to have a for loop, which in this case was just trying to run, I don't know, 400,000 times. I don't want my for loop to segfault me and kill my program with an unrecoverable out-of-memory error. Because like I said, if you stack overflow, you can't recover from it. Because to recover from it, you would need stack space, and you are out of stack space. And so it is just death to your program. There is nothing you can do at that point. Just delete yourself and start over. Okay. So I am personally not a huge fan of recursion, but there are definitely times when recursion allows you to make a very beautiful program. Now, let me give you a terrible implementation of Fibonacci. Okay. Are you guys familiar with the Fibonacci sequence? It goes 0, 1, 0. Optionally, sometimes you count from 1. 0, 1, 1, 2, 3, 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 21 plus 13 is 34. 34 plus 21 is 55. 55 plus 34 is 89, etc., etc. So each entry in the Fibonacci sequence is equal to the sum of the two previous numbers. Very famous sequence. And so there's a very beautiful and extremely inefficient and slow and terrible implementation of Fibonacci that uses recursion. So we can say if x is less... Actually, let me give you a bad version. Give you a bad version, see if you can figure out why it's bad. Okay, so if x is equal to 0, let's do this. Okay, we will return 0. If x is equal to 1, we're going to return 1. What are these two things here called? It's like an end zone for our program. What do we call it? The thing that stops us from looping forever. What is the name of these things? It's on the screen. What do we call the backstop, the end zone, the goal that we're reaching towards, the stopping point, the bus stop? I don't know. I'm running out of the base case, correct. Okay, so this is one base case. And we've got, another base case. All right. Bay case is even better than a base case. Okay. And then we have the inductive step. The inductive step must always move towards the base case. Okay. So we're going to return the Fibonacci of x minus 1 plus the Fibonacci of x minus 2. What would happen if we just had x here? So the Fibonacci of 5 is equal to the Fibonacci of 4 times the Fibonacci of 5. Well, what is the value of the Fibonacci of 5? Well, the value of the Fibonacci of 5 is equal to the value of Fibonacci of 4 plus the Fibonacci of 5. We have an infinite loop. Do you guys see that? This is a bad inductive step because we are not always moving towards the base case. The first one is, the second one is not. And so this is an infinite loop right now. Okay? So to fix that, we have to make sure we always move towards it. Now I put a little asterisk there because you can do like probabilistically moving towards the base case. Like 75% of the time it moves towards 25% of the time it moves away, and those kinds of algorithms make me feel very nervous, because you can't guarantee they'll end, but they probably will end. Hopefully, as long as your random number generator is good enough. So that's it, though. So if we wish to for int I equals 0, I is less than 10, I plus plus, see out the Fibonacci of I. This code here is going to give us the first 10 Fibonacci numbers. See that? 0 and 1, 2, 3, 5, 8, 13, 21. Okay. Now, there's 2, 3 problems with this code. Anyone seen it? Any of them? So there's three serious problems with this code. Anyone see any of them? It seems to be working. Right? When I passed in 10, yeah, I got the first 10. The cout fib I is fine. Main is completely fine. The function itself is wrong. Could it go out of bounds? You tell me. Don't ask a question. But there's no bound. There's no vector. There's no array. There's no bounds to go out of. What do you mean by going out of bounds? I mean, yes, but what do you mean by out of bounds? X will progress beneath 0. It shouldn't. The smallest number x can be is 2, and it's going to do 2 minus 2 is 0, and the base case will catch it. But it is not, in fact, true that x is the lowest number possible is 2. What if I passed in a negative number? What if I couted the Fibonacci of -1? Who would do that? Who would do such a thing? What kind of monster would pass in -1 segfault coordinate? This is why you always have to vet your inputs. Every time somebody gives you an input, even if it's you need to make sure you are handling it correctly. Okay? So, basically half of all integers are negative, and we're handling none of them. We're, maybe the minimum integer would underflow around and work, but basically, we just forgot about half of all possible numbers. And so how do we handle this? How would you handle it? How would you, it doesn't even make sense. Give me the -1th, entry on a sequence. That doesn't even make sense. It's like having a negative height, or, you know what I mean? Like a negative weight. It just doesn't really compute. So what would you do if the person asked for the -1th sequence in the Fibonacci sequence? What would you guys do? Cout error? Sure. Show what I would do. Pretty simple change. Just return 0. They ask for something off the left, I just return 0, maybe. But yeah, couting error is probably pretty good. If x is less than 0, die, something like that, right? Yeah, probably a good idea. Make the parameter an unsigned integer. Yeah, that's another way that I would probably do it. I don't like unsigned integers though, but in this case, it seems like the right, the right move. So, okay, well, we can't have numbers less than 0 now, so it's solved. Okay. What other problems are there? Just core dumped again. Eh? What? Where did we core dump? How did we core dump? Kind of like my solution of just returning 0 better, but If you pass in -1, then it's gonna underflow up to max int. Did it wrap around? Yeah, it did. It wrapped around to maximum integer, then it seg faulted off of too deep a recursion, right? So it's still not handled right, you know. So that's a problem. You know what I mean? Probably you should just say, let's just do integer x, and if x is less than 0, or x is greater than 20. Run an error, die, call it a day. Nice. Yeah, but this code still works. Good. You can make this all the way up to 20 before it crashes. Cool. What if we take it all the way up to like 60 or something like that? Up the upper range on here. Maybe this will help make it clear what the other problem is with it. Huh. Look at that thing slowing down. Look at that. Each number taking about twice as long as the number before it to compute. First ones are real fast. Now it's chugging. Look at how slow that's going. Like, ooh. Man, that's slow. Purchase a faster computer. Yeah, you doubled the computer, it'll compute one element in the sequence faster than the other one. Because what's happening here is we've accidentally created an exponential algorithm. We've created an algorithm where in order to compute the Fibonacci of 30, we have to compute the Fibonacci of 29 and 28. And to compute the Fibonacci of 29, we have to compute the Fibonacci of 28 and 27. And so that means we're going to be computing 28 twice. And then we're going to compute 27 like 4 times. And we're going to compute the Fibonacci of 26 8 times. And the Fibonacci of every level down you go, you have to do double the work. See that? And then we just got an overflow. That was the other bug that I wanted to show you. Perfect timing on that. I don't know if you guys saw that at the very bottom here. It overflowed. Yep. And so we can't even get up that high on the Fibonacci sequence because we run out of numbers, right? Integer is not that big. Perhaps you could store the previous result. In fact, I would highly recommend rewriting Fibonacci so that it is not recursive, but instead just using a for loop and maybe a vector or something like that. And then it is order n. This algorithm here is a really, really terrible order 2 to the n, which is called really stupidly slow algorithm. Everybody loves showing off Fibonacci as a exponentially slow algorithm like this. Okay? It's beautiful. It's beautiful mathematically. But it is every time you call fib, it calls fib twice. And so every higher number you call is going to more or less double the number of Fibonacci calls you make. So you're doing double the work every time you go up one number. That is called an exponential, non-polynomial, stupid, yeah, we'll just call it stupid slow algorithm. Okay? All right, so, and then of course we've got the integer overflow problem. Okay. So let's come back over here, and then we were stack overflowing as well. When we had passed in a big enough number, it would call itself. The stack's going like this, down, down, down. It hits the boundary, gets killed. Okay, that's another problem with it. Right? For loops are just a lot nicer. For loops won't help with this, by the way. For loops will not help with the integer overflow problem. So you should store it in maybe a long. That might buy you a little bit more time than an int, but ultimately you want to have infinite precision integers as your solution for that problem. Okay, so let me switch over to a presentation I have on this. You guys have any questions about recursion? Your homework assignment's called Zeta. I decided to give you guys a pretty low-key homework assignment. I typically give it as like a warm-up exercise for CSI 41 because it just kind of like uses all the different components of C-side 40, but you guys already know all the components of C-side 40, so you can do it. The zeta function is essentially like give me a function of f of x that counts all primes up to x. So if I passed in 10, if I say what is the f of 10, how many prime numbers exist up to the number 10? What do you return? How many prime numbers are there up to 10? Or we can do like something like this, where it's like 10 to 20, or something like that. How many primes between 10 and 20? 11, 13, 17, 19. So the answer is 4. There are 4 prime numbers between 10 and 20. So your function will return 4. You got 9 days to work on that. Okay? So this is a homework assignment called Zeta. It's got a hints file. It's got some hints in it. If you want to have infinite precision integers, that's how you do that. If you're going to do primality testing, there's a function to do that. Or you can write your own using a for loop or something. So yeah, so basically you're going to type in a starting number, an ending number, and you're going to basically output how many primes are between the two numbers. That's it. You have 9 days to do this. It's not supposed to be hard. It's like summing them up or something. Okay. Yeah, it has something to do with prime counting. I don't know. There's like number theory things you can do with the zeta function. I don't really understand them at all. Okay. So you guys understand the stack now? Every time you call a function on the stack, it moves the stack pointer down, and that's how you allocate memory on the stack. And the opposite's true too, right? Like if you just have a regular function that gets called once, it's going to allocate enough RAM to have variables A, B, C, D, and Bob. And then when you return, the stack pointer moves back up, and all these guys go away. So it's very fast to allocate a chunk of RAM. It's very fast to deallocate a chunk of RAM. The pointer moves down, the pointer moves up. These values are not zeroed. And so if you want a demo of why you should always initialize your variables, we can do that for you. Print out the address of A. Maybe on the next line. So I'm going to print out the values of A, B, C, and D. So what value does A have? What value does B have? What value does C have? What value does D have? It's not rhetorical. Not rhetorical. I'm asking you guys. What values do A, B, C, and D have when I print these? What values are you going to expect to see here? Print out the value of x2. Something random? It's not random. It's not random. It's just whatever was there in RAM before. So let me tell you a story about my daughter when she's about 1 year old. She knocked over a bowl of spaghetti. And I walk in, I'm like, hey, how did that bowl of spaghetti get on the ground? And she's like, I don't know. That's the answer for like what value A has. I don't know. You have to do the thing with your hands too. Everybody say, I don't know. With your hands in chat. Was that the Nicolas Cage? What is that? 4 shrug, whatever that is. Yeah. I don't know. I don't know. So A is used uninitialized. I know. Thank you. I know. Thank you. So if you run it, you can see that A has negative 1.6 billion. B has the value of 0. Then we have 4.5 times 10 to the negative 41st power. The letter O. And then X has the value of 10 because I passed that in. So all these guys have a memory address, except this is, I don't know what's going on here. What is that? Oh, it's the memory. There. Okay, so you can see that all these guys are in the stack area of RAM. Stacks up near 7FFFFFF. See, all these guys are up in RAM. DAF8, DB00, DAFC. So this guy and this guy are 4 bytes away from each other. In RAM, DAF6 is 2 bytes. 9154 DAF8, 9154 DAF6. Only 2 bytes away. And then DAEC, which is going to be 16 minus 6. It's 10 bytes away. I think this guy. 9154 DAFC. 9154 DAEC. Yeah. Okay. So all these guys you can see are up in stack space. You can see every time we run it, we get different values. It's not random. You should not use this as a random number generator, for one thing. It's not random. It's just whatever was in RAM there before. So whatever value was in memory, that's the value they have when you have uninitialized values. Okay. So anytime you have an uninitialized value, the correct answer for what value it has is undefined. It's got a value. It has a value. You just don't know what it is. There's no correct answer for what value A, B, C, and D have. For X, it's 10 because that one actually has a value. We're passing in 10, and so X is properly defined. Everything's fine with X. But for A, B, C, and D, it is just super scuffed, right? Do not write code like this. It actually bugs me. Have any of you guys done the Zybooks, Scilabs, where they make you have uninitialized variables like this? It's just bad practice, man. Like, you just need to get used to doing this. You know what I mean? You do this. You never have any questions about it. It's always the same. It's deterministic. It's predictable. Even if you're like, well, I'm going to be reading and, I'm going to C into A, or something like that. Yeah, in the meantime, if you have it like this, A is not initialized, and people will sometimes do something like that where they use an uninitialized value to initialize something else. Or you can do that, which looks really stupid. You initialize a value with itself. Valid C++ doesn't make the slightest bit of sense. Valid C++ though. So if you initialize a variable to itself, that's interesting. Oh, check out the C on that. All right. Warning: B is used uninitialized. I know. Well, no, it's not uninitialized. Look, it's initialized. I initialized it to itself. Okay. All right. So that is kind of my talk on recursion. I do have a presentation on it, so let's cover this real fast. Fibonacci sequence. Yeah, there we go. So again, every recursive program needs 2 things: a base condition to stop it from looping forever, and an inductive step or recursive step that moves it towards the finish line. So everybody take a moment and look at this code and tell me, will this function always terminate successfully? Like segfaulting doesn't count, right? Will this function is trying to do multiplication via addition. It's supposed to multiply. If you multiply 4 times 5, it'll add 5 together 4 times. So take a moment and tell me, is this handling all possible numbers for A and B. What do you think? Are there any numbers that will cause it to infinitely loop? Negative, so there are no numbers that can give it infinite looping? Or are you saying negative numbers will cause it to infinitely loop? Will it infinitely loop? Negative. All right. If a equals 0, yeah. Like if you multiply 0 times 5, you should get 0, right? But this code is going to infinitely loop, and probably going to segfault with 0, and also negative numbers are also not. I don't want to say. Technically, if you had infinite stack space, what would happen if you called multiply with like negative 100? Then it would call itself again with negative 101, right? You guys see this right here? If you call multiply with a equals negative 100, it's going to call itself with a equals negative 101. And that one's going to call itself with a equals negative 102. And that one's going to call itself with a equals negative 103. You're like, oh, isn't that an infinite loop? No. It'll eventually probably underflow. Once you hit negative 2.1 billion and change, it'll probably underflow back up to 2.1 billion and then call itself all the way down to 1. So it'll probably do roughly 4 billion additions of B together, which is going to overflow B quite badly. B will probably overflow, however many times, like depending on the size of B. So, yeah, that's not good. You should probably handle it. Like, what should we do? What should we say if the person passes in 0 for A? What should we return? So the user wants to multiply 0 times 5. A is 0, B is 5. What should we put into our base case there that will successfully handle 0 to fix this code right here? What should we put in? I'm going to pause the recording so you can think about it. What should we add to this code here so that it will handle multiplication by 0 properly? If a double equals 0, return 0. Correct. Now, how do we handle negative numbers? So if the user says negative 3 times 5, we don't want to just return 0. That's wrong, right? Negative 3 times 5 is negative 15. So we need probably another special case handling A being negative, right? Because right now it'll just kind of infinitely loop. Technically, it'll eventually stop, and more technically, it'll probably just segfault after a couple hundred calls to itself. But how do we handle negative numbers properly? Yeah, there is a temptation to say if A is less than or equal to 0, return 0, but that's not correct, because negative 3 times 5 is negative 15. So, we do need to, in fact, handle negative numbers correctly. Yeah. Any ideas? How do we handle negative 3 times 5? If A is less than or equal to 0, return A? No. That'll return 3. Like if we have 3 times 5, we want it to return negative 3 and 5. We want it to return like negative 5, maybe? Yes. So if A is less than 0, then return negative B. And then when you do the recursive call, do it with the absolute value. And so you do one number of like negative 3, and then you change the negative 3 into positive 3 and just finish the loop that way. If less than 0, return negative B. And then for the recursive call, you want to recursively call in such a way that you will do the same. Like if negative 3 times 5, you just do 3 times 5, right? Like, same thing. But you just negative the result of it. And so that would fix it. Okay, so what does this function do here? I'll just tell you, this is merge sort. This is actually almost a functioning sort algorithm. It's missing one little thing to make this function work correctly. So what it's doing is it is going to do something called divide and conquer, which is something that every computer scientist needs to know how to do. This is actually what separates out experienced programmers from new programmers, is the ability to break a giant problem down into chunks. So when you're working on a project as a project manager, you're like, okay, you work on this part, you work on that part, you work on that part. The two of you guys talk to each other and work with the client on developing that part. And that's a important thing. And when you're in one of these classes, when you start getting homework assignments that are bigger and bigger, then you need to mentally understand, how do I decompose a problem? How do I break a problem down and solve each individual piece? And a lot of times we'll actually whiteboard it. Like, okay, we got a piece over here, and this piece, talks to that piece, and then this piece also talks to that piece, and then that piece talks to this piece. Like, we'll diagram it out, and then we'll just mark off like one of these chunks at a time. This is what I'm working on this week. I'm working on the collision engine in my game engine, so the two things can touch each other. And that's going to feed into the event system. The event system needs to know when I touch something so it can trigger something. Okay. Well, that requires knowledge of, I don't know, the map system or whatever. So this notion of decomposing a problem is extremely important. So what we're doing here is we have an array, and we're going to start off by saying just sort the array. So we've got 10 numbers, right? 0, 1, 2, 3. Different numbers in here. And we're gonna say, sort the array starting at index 0 going to index 10. And then it's going to split this array into two halves. It's going to split into a left half and a right half. And there is one little bug here that I want to see if you guys can spot. So we're supposed to split it into two halves. You guys see what the problem is? Pause the recording so you can take them. All right, well, that was fast. I didn't need to pause it. Yeah, this needs to be q plus 1. So where's my mouse at? Where's my mouse? There we go. Okay. This needs to be q plus 1. Because right now, if we sort from 0 to 10, it's going to recursively call down sort from 0 to 5, and then also sort from 5 to 10. And so this spot here is going to get duplicated, and even worse, it's not going to terminate, because when you get down to p is equal to 1, r is equal to 0, this part here is going to say sort from 0 to 0, which is the base case. It'll stop. This one will recursively and infinitely loop, saying sort from 0 to 1, sort from 0 to 1, sort from 0 to 1, infinitely. So all you need is a little plus 1 right there, and then the code's correct. And this is, in fact, merge sort. So that thing there is called a sorted merge. Sorted merge. It's in the std library. And what it does, it merges two sorted arrays together. So if you have one array holding 10, 11, 20, 30, and another array holding 5, 6, 15, 25, to do a sorted merge, if you have two arrays that are both sorted, you can actually combine them in order in time. And so what you do is you just look at the first element of both of them and pick off the smallest, and then just advance that one to the right. Yeah, 6, advance to the right. So who's smaller, 10 or 15? 10 is. Move to the right. Who's smaller, 11 or 15? 11 is. Move to the right. Then we're going to have 20. We're going to have 25. We're going to have 30. Okay. And that is a sorted merge. Okay. And then the part up here splits it in halves and halves and halves and halves. So what happens is you sort from 0 to 10, which turns into a sort from 0 to 5, and a sort from 6 to 10. 0 to 5 is going to split into a sort from 0 to 2, and a split from 3 to 5, and 0 to 2 is going to split from 0 to 1, and the number 2, 0 to 1 is going to split into 0 and 1. An element by itself is sorted, right? So, the number 10 by itself is sorted. And so what you do is you divide it into a bunch of subproblems, and then you merge them together. And this gives you a provably optimal sorting algorithm, general sorting algorithm that works nicely. It's easy to code, and it's provably fast. So how many times can you do this recursive division? Like if you're dividing by 2 every time, if you go from 8 to 4 to 2 to 1, how many times can you divide a number by 2 until you hit 1 or 0? Anyone know? 16, 8, 4, 2, 1. 20 turns into 10, 5, 2, 1. How many times can you divide something by 2 until you hit 1? Anyone know, mathematically? It's a logarithm. I told you guys, logarithms are actually useful in computer science. So it's the log base 2 of n. So if you have a million elements, the log base 2 of n is approximately 20. So 20 times it's going to divide itself down, and then 20 times it's going to join all million elements together. So joining elements takes order n time. There is a log base n times you do that. So log n times n means the total running time of this thing is n log n. And this is provably fastest sort. There's a number of number 1 sorts that are all order n log n, but you cannot do better than that for general numbers. There are faster sorts, like Stalin sort, where you delete anything that's out of order. That's order n. Stalin sort's very fast. You just lose half your data. There's radix sort that you can just count how many times each number appears. So if you're only sorting the numbers from like 1 to 6, and you've got millions of numbers from 1 to 6, you just count how many times the number 1 appears, how many times number 2 appears, how many times number 3, number 4, number 5 appears, number 6 appears, and that's it. You just output 1 million zeros, 2 million ones, 500,000 threes, whatever. And that's faster, but only if you have limited numbers. So for general purpose sorting, nothing is faster than merge sort, at least in terms of big O. Okay, that is called divide and conquer. All right, divide et impera. Split a problem into smaller tasks, solve the smaller tasks, then reassemble into the big. Okay. That is what separates old programmers from new programmers. Old programmers know how to break a problem down, solve each individual piece, and then reassemble into something that works. New programmers, you're still just working on like making an if statement work. You know what I mean? So, okay. No, I do not. Keep these ink annotations. So your lab time for today. And once you get it done, you can just leave. Just message me. It's not supposed to be hard. What's up, girl? You got some pumpkins and something? What'd you get? What kind of?
Oh, we got these like little stakes. These little stakes that say like. Look, I'm just gonna show you.
Okay. So for your lab time today, you guys are gonna have to rewrite FizzBuzz so that it is recursive. For the Zeta assignment, you should also probably try to do it recursively. You don't have to, but it's probably a good experience for you. Okay. My input tester doesn't test whether or not you solve it recursively or iteratively. It doesn't care. All it cares about is output. But considering that we're learning recursion right now, it's probably a good idea to try to do it recursively if you can figure it out. If not, not a big deal. Okay, we got some signs here, some spooky signs: Black Cat Crossing, Pumpkin Patch, Trick or Treat Street. There you go. Vampire Valley, Count Dracula Drive. All right. 1,
And we also got some
2,
fake spider.
3. Fake spiders? Why do we need fake spiders, girl?
No, fake spider webs.
Okay. All right, very cool. Thank you, girl. Okay.
And we saw the decorations from last year.
All right, I'll be on in a sec. Okay, so if you guys can get FizzBuzz done in the next half hour, done recursively, you're done. You can leave. There is no class. There's a recorded class on Friday. Okay, so you guys will watch the recording of me talking about stuff and take a quiz on Friday. Okay, there will not be a live class session on Friday. So what we're doing right now is your lab time. If you don't get it done, you got to go to the makeup with Mincarelli on Sunday, and he's going to have you do 3 recursive algorithms instead of 1. So try and get it done in the next half hour. Save yourself some work. Then get started on Zeta. Zeta is your next homework assignment. It's not supposed to be too hard, but you got 9 days to do it. So just get started on it now. Okay, that's it for today, guys. Thanks for coming out. Peace out.